Thanks for a nice introduction. It's my honor to be invited to give a talk in this nice workshop. After hearing a nice talk given by Po Chu, I would like to jump into another research field, which also requires low temperature environment. And the title is Non-Fermi-liquid Behavior Close to a Ferromagnetic Quantum Critical Point. My research is supported by Chien Lung Huang University, and especially Q4 and NSTC and Ministry of Education in Taiwan. Before I present my work, I really want to take this opportunity to thank Po Chu's effort in the discovery of high TC, and there is a reason. Let me explain this to you. So only if you are old enough, you will hear this name called Woodstock. So Woodstock is pretty much like the Coachella in nowadays. It's the musical event. And there's the so-called Woodstock of physics high temperature superconductivity happened in 1987. So annually in the United States, in March, there will be a so-called March meeting held by American Physical Society. In 1987, in the meeting room, three physicists, Mueller, Po Chu, and Tanaka, they presented the discovery of high TC. And in that meeting room, there's a pile of people. So that's why people call it a Woodstock in physics. It's a pity I couldn't be there, but I guess I will learn nothing because I was only 7 years old back to 1987. But thanks to knowledge, if you are also interested in this work, you can easily find it in YouTube. It's really surprising. So yeah, that's Po Chu. So because of this discovery, that inspired of young scholars, including my PhD supervisor, Yang Hongden Yang, who went to the United States to pursue PhD degree also in superconductivity. And because of him, I had a chance to also work on superconductivity. But as you might have learned from last talk, it is so difficult to keep going on research of superconductivity, so I decided to switch the field to the talk I'm going to present to you. So I will make an introduction to a quantum critical point, QCP, and then I will do a comparison between the antiferromagnetic versus ferromagnetic QCP. And I will show you two pieces of experimental data for the discovery of FM QCP in first, a local moment ferromagnet, cerium, titanium, vanadium, germanium 3. And second, a nickel-rhodium alloy, which is an itinerant ferromagnet. Then I will make a summary. So when I show you the quantum critical point, it's all about a phase diagram. So this is a generic phase diagram drawn by hand. We have a temperature versus delta. So this delta could be pressure or chemical substitution or magnetic field, depending on the systems. And inside this blue region, we have a magnetically ordered phase. So it could be antiferromagnet or ferromagnet. And outside of this region would be the magnetically disordered phase. If I vary the temperature along these red arrows and to lead the system to go across this phase boundary, this is so-called a classical phase transition. You are probably more familiar with. And if somehow I can introduce delta and to suppress the ordering temperature down to T equals 0, and I start to play around across this phase transition, this is so-called a quantum phase transition, and where the magnetic order is destroyed by quantum fluctuation. By the way, over here, the magnetic order is destroyed by thermal fluctuations. And in terms of phase transition, it could be a first order or second order. And for the second order quantum phase transition, we give it a name. That's called a quantum critical point. And if now I take a system that has been tuned to the quantum critical point and I start some measurements in the finite temperature region, what I will see would be inside this quantum critical regime, I will see non-Fermi-liquid behavior and universal scaling of thermodynamic properties. So this is pretty much the phase diagram I want to talk about today, but I would like to also link this physics to the unconventional superconductivity. So I show you three phase diagrams of three different superconductors. it's always, vertical axis is always temperature, and horizontal axis would be different, like a whole doping in cuprate. This is chemical substitution, and this is pressure. Besides the fact they all look colorful, these three superconductors, cuprate superconductors, you have heard of, iron nicotide superconductors, and recently very hot charged density wave with flat band superconductor, cesium chromium 3 antimony 5. Without tuning, the parent compound is not superconducting. This is the first signature they have shared. And second signature is when a superconducting dome shows up, underneath the superconducting dome, there is always a quantum critical point over here, here, and there. So the fact that when the quantum critical point shows up, and on top of it is very close to the maximum TC in the superconducting dome, that naively did me think that somehow quantum fluctuation may mediate unconventional superconductivity for this kind of superconductors. But how, I don't know. I just show you the nice results. Spoiler alert, the materials I'm going to present today don't have superconductivity. Okay, now next will be the comparison of the literatures. So when I look at the literatures, there are many antiferromagnetic quantum critical points. There have been 2 reviews of modern physics papers discussing, to summarize all the materials. So I just list some famous ones. And for the elements marked in blue, that are the magnetic elements, like cerium, ytterbium, chromium, and uranium, and so on and so forth. There are a lot. But if I look at the ferromagnetic quantum critical points, in my opinion, there were only 6, not more. And there's a reason for that, why we could have only few ferromagnetic QCPs, but a lot in FM. So quickly speaking is that there are non-critical modes always exist, but they only couple to Q equals to 0. So Q is a wave number which describes how moment modulates. For AFM, Q is not 0. So AFM, the order parameter fluctuations of AFM will not couple to this non-critical energy. But ferromagnet will couple, and that coupling will result in the failure of formation of a FM QCP. So when people try to tune a ferromagnet, that's often the result. Either the second, so this is temperature and this is tuning axis. The second order phase transition will terminate at a tricritical point, TCP, and the transition becomes first order. So if it's first order, it's not a QCP. And if you apply field, you will form this fishtail-like phase diagram. And when people try to use disorder, chemical substitution to tune the system, sometimes the disorder effects are too strong that the phase boundary will be smeared out. So again, there's no QCP. And sometimes it's even more exotic. The magnetic ground state changes from ferromagnet to antiferromagnet. So my question is, can we find a route to reach an FM QCP? That's my motivation. And the answer is probably yes. So 3 physicists, Blitz, Kirkpatrick, and Voita, BKV, they proposed we could actually smartly take the disorder on purpose as a control parameter. And this is how the trick plays. So if I told you, for a clean ferromagnet, that's often the case. The second order phase transition, if you tune it, it will end up by the tricritical point and continue by this fishtail, the first order transition. If we put a little amount of disorder, the TCP temperature will be reduced. And also the area of this fishtail also reduces. Finally, at a certain point, TCP will end up at T equals 0. And if you look at this phase diagram, this looks very similar to the generic phase diagram I've shown you a few slides before. So my work would be to test if this theoretical prediction works. So this is the first target compound I work with. The parent compound is cerium titanium germanium 3, which has a hexagonal structure. And it's not new. So people know it more than 10 years ago. This is specific heat data versus temperature. And if you look at, so this is 14 Kelvin. At 14 Kelvin, there's a jump. That's cerium titanium germanium 3, which orders